Hello there, welcome to the channel. We're looking at some publicly available questions for AP Physics Course C, Mechanics specifically. In the diagram you see a contraption where we have two blocks. One is horizontally on the table that is not frictionless, and block 2 is connected to it with a string, massless string, over a massless and frictionless pulley. And they're asking us in the contraption you also see motion detectors, so if this contraption moves, then we can analyze speed and whatnot. But the first part of this question, A, asks us to find the minimum coefficient of static friction that would allow for this contraption to stay at rest if we release block 2. So if I were to check, we would have mg, normal force, force of tension, and force of friction static. That would be the free body diagram for block 1. Block 2 is hanging, so it only has two forces. It has also mg and that very same tension, and this tension and that tension are identical. So therefore I can say that force of friction static on block 1 should be equal to gravity on block 2. Mu times normal force, and since it's just flat and there are no vertical components of any force other than gravity, it's going to be mu mg. This is 0.44, should be equal to 0.2 times g cancels, and we end up with mu static. The minimum coefficient of static friction can be found as 0.2 divided by 0.44. There we are, we answered question A. In part B, this contraption is in motion, so therefore static friction is overcome, and we're dealing with kinetic friction. These two motion detectors are giving us the acceleration of block 1 and block 2. And you see how one acceleration is positive and the other one is exactly the same but negative. In terms of magnitude, they're the same, about 2.31 meters per second squared. Why is that? Because positive is away from the detector. Block B is moving away from motion detector 1, so therefore acceleration is positive, but block B is approaching motion detector 2, so therefore its acceleration is negative. And they're asking us to draw a free body diagram, which I already did. You see it on the screen. Tension on block 1 and tension on block B should be the same, but force of gravity is greater than tension for 2, and then tension is greater than friction, kinetic, for block 1. And then they ask us to figure out again mu, but this time it's mu kinetic that we're after. So both of these are in motion right now. So we're gonna set up a system of equations. For block 1 is going to be m1 times acceleration should be equal to tension minus mu kinetic times m1g. Block 2, it's also accelerating, and in this case we have m2g minus tension. If we add these two, because it's a system, we can. A times m1 plus m2, tension cancels, and this is going to be m2g minus mu k m1g. Rearranging, mu k is going to be m2g minus a m1 plus m2 divided by m1g. And then let's plug in our numbers. I got 0.11. Now D, they're telling us, you know what? When experimental testing was done, it turned out that mu k was actually greater than mu k theoretical. And as one of the reasons that they're suggesting, there is an incline in the table. So let's look back. What is it that they're measuring? They're measuring the acceleration, which is net force divided by the total mass of this whole thing. And if the table is inclined, which way was it inclined, by the way? What do you think? Like this? Or was it inclined like that? If we have an incline like this, then we have this extra mgx, which is part of the m2g minus friction. And that is going to be mg now cosine, right? Cosine of theta, whatever that theta is right here. So if we do have an incline downward, we're going to have a lower force of friction. That mu right there would be actually less. What we ended up was mu kinetic was actually greater. Why is that? In this situation right here, we would have this opposing force. So net force would have been force of gravity m2g minus mu mg cosine, and then minus mg, this is m1 times sine of theta. So this is lower, and because that is lower, we're thinking that friction is greater. So that would be the reason why experimentally we ended up with a greater coefficient of friction than it actually is theoretically. In part E, we continue experimenting with this contraption here, but we are rearranging so that the weights, the extra weights from block 1 are put onto block 2, and that increases the acceleration. Plus, we transfer this to the surface that basically has 0 force of friction, and they are asking us to figure out g, the value of acceleration due to gravity, using this graph. First, we're going to draw a line of best fit. So that allows me to use, they always give you a range of acceptable values. So depending upon how you draw your line of best fit, so long as it looks like a line of best fit, you'll be fine. I'm going to find the slope. So acceleration for our system is going to be m2 times g over 0.64, which is the total mass. This graph is a versus m2, right? So I can rewrite this as g over 0.64 times m2. This right here is the slope. Then g is going to be 17 times 0.64. Ooh, maybe you have a better line of best fit that is more realistic. Mine ends up with like almost 11, 10.8 meters per second squared. In F, they're saying, what if we take this contraption here and we incline it so that the incline looks like this? Well, then remember how I showed it before, because you will now have the component of gravity acting in your interest. Normal force is not going to be less, and therefore force of friction is going to be less. So then your net force is going to increase. And since net force is going to increase and the total mass is the same, then your acceleration is going to increase. There you go. That concludes this lovely example. If you have any questions, put them in the comments below. If this was helpful, like, subscribe, share, be kind.